Subject AC machines. Topic single phase transformers. Subtopics transformer on load condition. So in this previous class we learned the working of ideal transformer on no load was discussed, and also the primary current on no load was only to set up flux in the core and to meet the iron losses. In this session, the change of currents and flux in the core and voltages when the transformer is loaded is to be discussed. So here in this objective, on completion of this period, you will be able to know what is an ideal transformer, the operation of transformer on load, and the development of phasor diagrams. The development of phasor diagrams. Now, in ideal transformer, the theory of operation of a transformer is best understood by viewing the transformer as an ideal device. So, in an ideal transformer has no losses. The primary and secondary windings have zero resistance. The leakage of the windings is zero. The permeability of the core is infinity. Now, the transformer on load. When the transformer is connected to supply source, the primary winding drawing current I0 sets up a flux in the core is as shown in figure. Here in this, see here, this I0 will set up the flux, this flux. I0 will set up the flux. Here, this is the I0 from the supply side and AC supply. The flux in the core is pi. The flux in the core is pi. This is a steel core, and this flux is in two limbs. It is closed pathway, and the primary side turns N1 and secondary side turns N2. So see here, this is so ideal transformer when the primary is only excited, the primary is only excited. here when the transformer is loaded, the secondary current I2 is set up. That means I2 is draws to the load. The current I2 draws the load current. So the I2 is set up its own flux by 2. So here this setup flux pi 2 is opposes the main primary flux pi. In this as shown in figure, here the pi 1 is the main flux and here the pi 2 is a secondary side flux. So here this is pi 1 is main flux in the core. When the load is connected at the secondary side, the current I2 current is drawn at the second side. This current will be set up the pi 2 flux. This flux and this pi 2 flux is opposes the pi 1. See in this diagram, pi 1, pi 2 are both are opposite to the direction. Pi 1, pi 2 are both are opposite directions. So, figure 2, transformer on load pi 2 is established. So, when the secondary flux here pi 2, secondary flux means here pi 2, so opposes the primary flux, the reduction in the net flux in the core. When that means here the pi 2 is opposing pi 1, immediately the main flux will be, resultant flux will be reduced. So here the core is causes to draw an extra current from the supply known as load component of primary current I2 dash. When net flux is reduced immediately from the primary side, it draws the extra current from the supply. That is called I2 dash here. I0 is no load current, which is for set up the flux in the main flux in the core, and I2 dash is additional current to draw the additional current in the primary side. So this additional primary MMF into I2 dash set up a flux by 2 dash, which is equal to, that means equal and opposite to the flux by 2. Here see here, here two fluxes are producing. From the secondary side pi 2 is producing, from the primary side the pi 1 dash is producing. These fluxes are opposing. The main flux is pi, so pi 2 and pi 1 dash will be cancelled. Then here the remaining of main flux is be here in the passing through the core. Here pi 2 dash is neutralize the pi 2. So that means pi 2 dash and pi 2 both are opposite and same magnitude. So these are subtracting, that means it will be neutralized. Then when these are neutralized, pi 2 dash minus pi 2 will be 0. Then after remaining flux will be only pi. So here, since pi 2 equal to pi 2 dash, the net flux in the core is pi. So therefore the same as it no load as shown in figure. So here therefore I1 equal to I0 plus I2 dash, I0 plus I2 dash, I1 is equal to I0 plus I2 dash. See here in this core, this is the practical transformer, single phase transformer. I1 is equal to I0 plus I2 dash. So here net flux in the core is same flux, that is pi. Since pi 2 equal to pi 2 dash, the secondary MMF equal to additional primary MMF. Secondary MMF is equal to additional primary MMF. That is N2 I2 is equal to N1 I2 dash. Since the reluctance for the two windings is same. Since the reluctance for the two windings is same, I2 dash equal to N2 by N1, that into I2. So I2 dash is equal to K into I2. I2 dash is equal to K into I2. So that means here I1 bar equal to I0 bar plus I2 bar. The total primary current is the vector sum of I0 and I2 dash as shown below. So here, see here, this I1 is divided into I2 dash and I0. This I0 is divided into I mu and IW. So where I2 dash is the load component of primary current, I0 no load current, I mu the magnetizing current or wattless component of no load current, IW the working or active or iron losses component of no load current. So here the phasor diagrams based on the knowledge of various primary currents and secondary current and the voltages of the two windings. The phasor or vector diagram of a transformer can be drawn for all types of loads. So here a resistive load, that means unity power factor, inductive load, that means lagging power factor, or capacitive load, that is a leading power factor. A leading power factor. So here, see here, I1 V1 pi and I2. Based on this, so we can say unity power factor and lagging power factor and leading power factor. So here the resistive load means here at the load side is E2 and I2. E2 and I2 E2 and I2 both are in phase. E2 and I2 both are in phase. See here, this I1 is addition of I0 I2. So here this combination, so I0 I2 is combination is nothing but I1. Here this is the I2 and E2 both are in phase. So here the flux is the reference. This is the IMU, both flux and IMU both are in phase. So the IMU is lagging 90 degrees with reference to the V1, and this E1 E2 is lagging the 90 degrees with respect to the flux. So this is based on we can draw the phasor diagram. For this resistive load I2 E2 both are in phase. So now go for I1 is I2 addition of and this I0. So this phasor diagram for resistive load. Now inductive load, see here the flux is a reference. This flux is a reference, and here see this, compare this one. Here E2 and I2. Here the current is lagging by 2 degrees with respect to the E2. So this is for inductive load. Then when I2 is lagging, project this one which gives the I2 dash. Here the I1 is combination of I0 and I2 dash. So when this vector sum will give the I1, I0 I2 which gives the I1. So the projection of I2 is nothing but I2 dash. Here V1 I1 is angle is pi 1, and this I0 is between the V1 and I0. See here this phasor diagram for inductive load. This phasor diagram for inductive load. See here for capacitive load, here in capacitive circuit, in capacitive circuit, the current is leading by pi degrees. Current is leading in the circuit. So here the current is leading by pi 2 degrees. So by with respect to the E2. See here when projecting I2 is come in this way, I2 dash. So here the flux is a reference, and V1, this one V1, this I1 is the vector sum of I2 and I mu. This I1 is nothing but I2 and I know is gives the I1. So here this is the current is leading with pi 2 degrees in capacitive load. In generally always the 99% of applications, so only inductive load, not capacitive load. So here only this is considered in capacitive load. The phasor diagram for this is for capacitive load. The following figures shows the phasor diagram of ideal transformer for inductive load where the no load current I0 is neglected. See here, in generally for inductive load I0 is neglected. So here in generally, see here for inductive load, this is a phasor diagram. E2 and I2, I2 is lagging. When I2 is predicted in this way, will give the I2 dash. Here I0 is neglected. The load current here I0 is neglected as compared with the load current. So in this way we can write I1 is equal to I2 dash. I1 is equal to I2 dash. Here the pi 2 means the phase angle between the E2 and E2. This phase angle is lagging. Here also this is the angle is pi 2. So here the phasor diagram of ideal transformer for inductive load. When I0 is neglected, when I0 the case is here and I0 is neglected, this is the phasor diagram. Here I2 dash by I2 is equal to, that means I1 by I2, that is equal to N2 by N1, that is equal to K. I2 dash by I2 is equal to I1 by I2, that is equal to N2 by N1, that is equal to K. So as no load current 2 to 5% of rated currents, that means full load current. Here no load current I0 is 2 to 5% of full load current. It can be neglected. So we can write I2 dash by I2, that is equal to I1 by I2, that is equal to N2 by N1. Therefore here I1 is equal to I2 dash. When it is neglected, I1 is equal to I2 dash. So the above relation is the basis of current transformer, which is used for measuring large currents by low range ammeter, as it is impracticable to connect an ammeter directly in the circuit. So once again, so we see here for resistive load E2, I2 both are in phase at load side. So I2, that means when projecting I2, which gives the I2 dash, this is I2 dash. The combination of I2 dash I0, which gives the I1. So here this is for the resistive load. And next is inductive load. Here the current is lagging with pi 2 angle with respect to the E2 behind the voltage E2. So when I2 is projected, it is I2 dash. I2 dash and I0, which gives this combination results will give the I1. So this is the inductive load circuit phasor diagram. And next one is here, this is for phasor diagram capacitive load. So here the current I2 is lead, and here the with respect to the E2, current I2 is leading with by 2 degrees. When I2 is projected in this way, it is I2 dash, I2 dash, and this I0, which combination gives the I1. This is phasor diagram for capacitive load. So when I0 is neglected, that means I1 is equal to I2 dash. So when I2 is projecting, which that means I2 dash, that is equal to I1. So the phasor diagram for this is for inductive load. See here, in inductive load, so it is 2 to 5% of rated or full load current. The no load current is 2 to 5% of rated current or full load current. So it can be neglected. Therefore, I1 is equal to I2 dash. That can be written as I2 dash by I2 is equal to I1 by I2. That is equal to N2 by N1. That is equal to K. So here it is used, this relation is used in current transformer. The reason is ammeter is not connectedly directly, so by connecting CT current transformer to the feeders or bus bars, we can measure the high current from this concept. So here summary, we have discussed about the operation of transformer on load and the phasor diagrams of the transformer at different studies. So UPF, unity power factor, lagging and leading power factors. So here the quiz, go for quiz. The flux in the core of a transformer at 0.8 power factor lags 1 milliwebers. Therefore, the flux in the core at unity power factor will be 1. The no load power factor angle of an transformer is about the, so it can depend on the 90 degrees. It is 90 degrees. The mutual flux in the core of a transformer is always constant. It is always constant, not varies with the load. The primary current of a transformer is, now do this problem at work. The core and copper losses of an ideal transformer at no load and full load respectively are, so core losses are not varying, only copper losses are varies with the load. So here the core losses is constant. So minimum, maximum. Oh, in ideal transformer it is 0. In practical transformer it is minimum and maximum. In practical, this is the answer. This is in ideal transformer case. So I1 by I2 is equal to K. Answer is I1 by I2 is equal to K. Frequently asked questions. Ideal transformer, explanation, operation of ideal transformer. Why the flux is constant in the transformer core. Vector diagram of transformer at UPF lagging and capacitive loads. Thank you.